All right, well, hello, my young friends. Hope everything's going well. I've had a few questions about an upcoming exam because you're thinking farther ahead than I am. So there's an exam scheduled for next Saturday, February the 27th. Format will be exactly the same. There's a question as to how much of the stuff that's on practice exam 2 we're going to get to between now and then. When I planned out the course, I had hoped to be done with chapters 7 and 8 by next Friday. I do 7 and 8 together because they're related to each other and it's easier to do it together than to do it piecemeal. In any case, I normally spend 5 or 6 lectures on chapter 7 and 8, and starting today we've only got like 4 and we still haven't finished chapter 6. So it is unlikely that we're going to get through chapter 7 and 8 completely. I won't know exactly how far we're going to get till next Friday. So I realize that puts you in an uncomfortable position because you've got this practice exam that was written assuming we'd get to it all. And there are going to be some problems on there that are not going to be on the exam, and you're not going to totally know which ones those are until right before the exam. So you're going to have to trust me that I'm not going to test you on stuff that we haven't gotten to yet. The alternative is just to push back the exam until we get through the end of chapter 7 and 8, but that may be a mixed blessing because you'd get more time but then be responsible for more stuff. So I think we'll try to hold the exam exactly where it's planned on, that is next Saturday, and we will include part of but not all of chapter 7 and 8. If you need further clarification, and you want to ask again as time gets closer what I think will be on the exam, I'll be happy to answer that. Anything you want to ask now on that subject? Yeah, go ahead.
Is chapter 6 study guide still due tomorrow?
Is chapter 6 study guide still due tomorrow? I suppose technically yes, though I can push it back if people want more time, that's fine. The study guide for 7 and 8 I won't make due before the exam, but some of it will be on the exam. And again, I'll try to make it clearer how much as we continue onward. Other questions? Folks at home, I forgot to ask if you can hear, but nobody's saying I can't hear in the chat, so I'm assuming you're good. Chapter 6 will be pushed then. I'm happy to make it due on Tuesday if that's more to everybody's liking. I think we'll move on from it today, though. All right, so last we were talking about thermodynamics, which is why reactions happen. And I want to finish up on that discussion, and then we're going to talk about kinetics, which is how they happen, and we'll move into some examples of substitution and elimination reactions. But to remind you of where we were when we ended last time, I'd shown you this reaction in which we take this alkyl halide, the alkyl bromide, react it with a base. We break a carbon-hydrogen sigma bond. We make a new oxygen-hydrogen sigma bond. We break a carbon-bromine sigma bond, and we make a new carbon-carbon pi bond. And we talked about how you can get a sense for the thermodynamics of this reaction by first comparing the stability of the negatively charged things on either side of the equation. And we talked about how Br minus is much more stable than this alkoxide just based on comparing their pKa's. And we spent all of chapter 2 talking about what makes a molecule capable of tolerating a negative charge. And then we decided to compare the strength of the bonds that we break versus the bonds that we formed. And these are all bond dissociation enthalpies. This tells you how much energy you have to put in to break a certain kind of bond. And these numbers are remembered roughly, vaguely from whatever tables are in the book. They may not be exactly on, and that's fine for the sake of our discussion. Never have you memorize those kind of numbers anyway. But a typical carbon-hydrogen bond involving an sp3 hybridized carbon is about 90 kcals per mole in strength. That's how much energy you have to put in to break it. A typical carbon-bromine sigma bond involving an sp3 carbon is worth about 60 kcals per mole. So to break both of these bonds, you'd have to put in 150 kcals per mole. The new bonds that we make, the bond dissociation enthalpy for the OH bond is 100. The bond dissociation enthalpy for the carbon-carbon pi bond, you have to be a little creative on, because most bond dissociation enthalpy tables will tell you what the number is for a carbon-carbon double bond, which basically summarizes the following reaction, and that is where you separate both partners that were involved in the double bond. Each leaves with 2 electrons, and you separate them at infinite distance. So that number would be for both the sigma and the pi bond. So if you take that number from the table and subtract how much a carbon-carbon sigma bond's worth, you can get a sense for what the pi bond is worth. And it's worth about 70 kcals per mole. So if we want to know overall in terms of bonds broken versus bonds formed, how energy changes in this reaction, we can add up the bond dissociation enthalpies for the bonds we break. We're going to subtract the bond dissociation enthalpies for the bonds that we form. Why subtract? Because making bonds releases energy, breaking bonds takes energy. And so 150 minus 170. We expect this reaction to be downhill in enthalpy. Our estimate is around minus 20 kcals per mole, though that number does not take into account the difference in stability, the greater stability of Br minus versus O minus. And so we might actually expect this to be even more favorable. Reactions that are exothermic release heat. Usually, what does heat mean? Well, usually that means a temperature increase. What does a temperature increase mean in terms of the molecules? You can think of temperature as being the average kinetic energy of the molecules. In more solutions with higher temperature, the molecules are moving around and bumping into each other more rapidly. And that's where the energy that's released as a reaction goes downhill. That's generally where it goes. All right. Anything you want to ask about that? Yeah.
Drickwood, you said that the number is probably higher because Br minus is more favorable.
Yeah, it's probably greater in magnitude, I guess more negative, more favorable. Yeah. Others? So I mentioned this in the 1 o'clock class, and I want to mention it here because it's a misconception that I think we pick up from high school biology. You may have heard, it has been said by them of old time that breaking a bond in ATP releases energy. Have you ever heard that before? Somebody ever said, yeah, this is how your body does stuff, is it breaks the bond in ATP and that releases energy. That's technically incorrect, and I'll show you what people mean when they say that. But let's just remind ourselves that breaking a bond is always uphill in energy. Breaking bonds does not release energy. So I'll draw real briefly the structure of ATP for you. You don't need to write this down or memorize it. You can look it up if you want to know what it is. Here's the TP part of ATP. That's the triphosphate. Oops, I made a mistake already. Here is the adenosine part of the molecule. You've got the ribose sugar, and then you've got the purine ring, the so-called base. And again, don't memorize this structure, but this is ATP. And I'll show you a reaction from glycolysis, which is one of the metabolic pathways whereby your body extracts energy from glucose that it can use to do work, and in so doing oxidizes all of the carbons in glucose to CO2. So one of the reactions in glycolysis is to take ATP and glucose and put one of those phosphate groups from ATP onto one of the oxygens from glucose. You'll learn more about this in 352 and in biochem. For now, we just want to look at the bonds that are changing. Because I know you're not scrambling to copy this down, I'm going to use my evil copy-paste powers to accelerate this discussion. Again, I'm not going to ask you to draw this from memory. And the products of this reaction are ADP and then glucose 6-phosphate. If you've had some biology before and done some metabolism, this is the first step of glycolysis, and it is way downhill in energy. Delta G is something like minus, I forget, so I'm not even going to tell you, but it's like minus 10 or minus 30. It's a big difference, but it's very exothermic. Once you shunt glucose down this pathway, it's committed. So we can talk about why this reaction is downhill in energy. And if you look at the bonds that change, we've broken a phosphorus-oxygen bond, and we made a new phosphorus-oxygen bond. And there's a couple things that are missing here. We've lost a oxygen-hydrogen bond. We can pretend that that's here and it gets made up and it's equal in energy and whatnot. In any case, the reason this reaction is downhill so much is because this kind of bond is called a phosphoanhydride, and it is weak, whereas this kind of bond is called a phosphoester, and it is stronger. It may not be clear to you right now why that's the case. In 352, you'll learn that carbon anhydrides are weaker than carbon esters. So by analogy, phosphoanhydrides are weaker than phosphoesters. But the reason this reaction is downhill in energy is you're replacing weaker bonds with more stable bonds. So that's why ATP is an energy-rich molecule in the sense that it's high in energy, it has weak bonds, and when you break them and replace them with more stable bonds, that's downhill in energy and that's spontaneous. Okay? So as you're moving your muscles, I don't want you to be thinking, oh, this is great, look at all the ATP that I'm breaking apart. That's only part of the equation. The other part is I'm replacing the bonds I'm breaking in ATP with more stable bonds. All right? It may sound like semantics, but let me tell you, it's not even physically reasonable that breaking apart ATP releases energy. It doesn't. It's that we're breaking it apart and replacing it with something more stable. Got it? Okay, good. All right. So now we want to talk about kinetics and reaction mechanism. Kinetics is a term that means how a reaction happens and how fast. And the concept of a reaction mechanism is really closely related to kinetics. Mechanism deals with which bonds form and break and in what order. Which bonds form and break when and in what order. So this is easiest to talk about with an example. So I'm going to present a pretty simple example from chapter 7. It's a substitution reaction. And I'll show you the products. And then I'll point out that Cn minus or cyanide is our nucleophile, that methyl iodide is our electrophile, and that we've got these two products here. If we want to think about what has happened in the course of this reaction, we used to have a carbon iodide bond, and now we have a carbon-carbon bond. So overall, I break the carbon iodide sigma bond, and I make a new carbon-carbon sigma bond. The other thing is that I replace Cn minus with I minus. And again, that replacement isn't really captured with these bond dissociation enthalpies that we can measure, though we could look up pKa's for the conjugate acid. HCN is about a pKa of 9, whereas HI is a pKa of minus, I don't know, 11. So again, it's fairly, you would predict just based on stabilities of those conjugate bases that it's probably fairly downhill in energy to replace a carbon iodide bond with a carbon-carbon bond. And without looking up the numbers, I can tell you that this reaction is exothermic and downhill, very spontaneous. Now, you got a couple of things going on here. And the question is, how do they happen and in what order? So you could think of a couple of scenarios. First, you could imagine that you make the new carbon-carbon sigma bond first, then break the carbon iodide sigma bond. Hey, Scott, you looking for your flash drive?
Thank you.
Yeah. Second, you could imagine that you break the carbon iodide sigma bond first, then make the carbon-carbon sigma bond, and finally, you could imagine that you do both at the same time. Sort of three limiting cases. All right? So we want to talk about how you can tell the difference between these things. So let's imagine what making the new carbon-carbon bond first and then breaking the carbon iodide bond second would look like, okay? So we're just hypothesizing here, don't take anything for gospel truth yet. We're going to consider the possibilities and then ask what the data tell us. So, okay, if I make the new carbon-carbon bond first, I've got an sp3 hybridized carbon attached to four things, and making that new carbon-carbon bond first would probably involve approach of Cn minus towards the carbon, right? Because you're forming a new bond. There would be some as I approach that carbon-carbon bond, I'm going to have some, as I approach the new carbon, I'm going to have some electron-electron repulsion between my negatively charged nucleophile and the bonds that are already on that carbon. So it's probably uphill in energy to have this cyanide approach that carbon, all right? And then maybe afterwards I get to an intermediate that looks something like this, only now I guess the negative charge would be on the carbon. already that should make me uncomfortable because I've got 5 bonds to carbon. Yuck, right? And then maybe in the final transition state, I would have the new bond to carbon in place and iodide is on its way out. The delta minus here indicates that as these new bonds are forming, you no longer have a full negative charge on something. You're in the process of making a new bond. And similarly, as iodide is leaving, you don't have a complete negative charge on it until it's gone. So this would be another transition state, number 2. And presumably after that, you would get to your products, I minus and then H3CCN. Okay? So that's one possibility. Now, how do you feel about that? What do you think? If it makes you uncomfortable, why? It's whack, says someone at home. That's good. I do understand that one. Pretty uncomfortable. Yeah, the thing that makes us most uncomfortable is really the idea that a carbon bonded to 5 things could be stable. We've talked before about how carbon only forms 4 things, forms 4 bonds, because more bonds than that would require populating an antibonding orbital. Another explanation for why carbon doesn't tend to form 5 bonds is that carbon is small and 5 things can't get close enough to carbon to make really stable bonds. All right? So we're not feeling that good about scenario 1. Let's think about what scenario 2 might look like. In scenario 2, we're going to break the carbon iodide bond first and then make a carbon-carbon bond. So this would involve lengthening of the carbon iodide bond first. Maybe this would be our first transition state. And then you would have an intermediate where iodide was totally free. What would be left behind would be a now trigonal planar carbocation. Okay. sp2 hybridized carbon. And then in a second step, you would have the carbon. I'm sort of running out of space here, so I guess I need to shrink things. Oops. In the second transition state, you would have, the carbon cyanide bond forming. And then you would get 2 products. Okay? So how do we feel about that one? It seems more reasonable. At least we're not making a hypervalent carbon, a carbon bonded to 5 things. What do we think about this first step from transition state 1 to intermediate 1? Do you predict that's going to be uphill or downhill in energy? Uphill, why? Because you're breaking a bond, right? So that step is probably what we might call endothermic or uphill. And whether or not this is reasonable will depend on how far uphill that step is. And we'll talk later on about how to assess how stable a carbocation is and whether it's too uphill to be reasonable or not. What do you expect for the second step, though? Should it be uphill or downhill? Got to be downhill because you're making a bond. Okay. So if I were to try to draw an energy diagram for this reaction, and this is something that the chapter will explain in more detail, energy is on the x-axis. That's not the x-axis, thank you. That is the y-axis. And then on the x-axis is something we call reaction progress, which is just a generic measure for how complete the reaction is. You can actually tie it to a physical measurement, like the distance between a couple of atoms, but we're going to keep it generic and just say reaction progress or extent of doneness. I don't know, extent of reaction. In any case, we would have starting materials, which are listed up here. I'm going to abbreviate that with SM, starting materials. And then we've got products over here. So starting materials would be here. We said going to the carbocationic intermediate would be uphill, passing through a transition state. So this would be transition state 1. This would be your intermediate I. And then in a second step, going downhill to products, and this would be transition state 2. That's sort of what we would predict for how energy changes in this proposed mechanism or scenario number 2. And now we can start to make some predictions based on some things you know from general chemistry. The rate of the reaction, or how fast of the reaction goes, is going to depend on the highest activation energy. What do we mean by activation energy? That is the distance from the starting material to the highest energy transition state. All right, now I know I'm going to head off a question that always comes, and that question is, well, what if the second or the third step is actually the highest energy step? What then? And I will tell you there are ways of dealing with that, but we won't require any of them to deal with the chemistry in this class. So the rate of reaction is going to depend on the highest activation energy, which is this energy difference between, in this case, starting material and transition state 1. That's the step where we're breaking bonds. So we'll call that activation energy 1. This smaller difference would be activation energy 2. So the rate of the reaction, because activation energy 1 is much greater than activation energy 2, the rate depends only on activation energy 1. And because of that, we call step 1 the rate limiting or rate determining step. Sorry about the penmanship. Okay? Yeah?
So I know where the activation energy for the transition state 1 comes from. Where does the transition state 2 come from?
The activation energy from transition state 2 comes from the difference in energy between the intermediate and transition state 2. So I guess we had our starting materials, and then take away the bond. right.
And then get the intermediate that you get to the next over the, I guess, are you breaking the bond right there?
So if I understand your question correctly, it's in this second step we're just making a bond. So why does the energy go up in the first place? And the answer to that is, if you think about the carbocation, in the carbocation, the electrons in each carbon-hydrogen bond are as far apart as they can possibly get. Moving towards this transition state as you start to form the new carbon-carbon bond requires that flat carbocation to arrange itself so that now those carbon-hydrogen bonds are a little closer to each other. And if that happens a little bit before the bond forms, you can start to go up in energy only a little bit, and then you get the benefit of forming the bond. in general, we'll see in chemistry that rearranging geometry requires you to go uphill a little bit in energy. Other questions? All right, so rate determining, rate limiting step, or slow step would be this first one. Now, you may have learned, does that sound familiar from general chemistry, sort of review? You may have learned a little bit in general chemistry about writing rate laws, okay? The rate law for a reaction depends on what's involved in the rate determining step. Okay? And the way that, so let's look at our hypothesis. In our rate determining step, which molecules are involved? We have two starting materials. We have, just to remind you, the methyl iodide, and then we have the CN minus. So in proposed mechanism 2, what is involved in this rate determining step? Just the iodide one, right? So in chemistry, for individual steps of a mechanism, you can predict that the rate of, hold on. Okay, so because we've said that step 1 is the rate determining step, the rate that our product appears at, the rate of change in our product as a function of time, is going to be equal to some constant times the concentrations of whatever's involved in that rate determining step. And in this case, it's just the methyl iodide and not the CN minus. And the rate constant itself comes from the activation energy one. There are equations that allow you to calculate the rate constant. I think one of them is the Arrhenius equation, where there's a pre-exponential factor and the number e raised to something. Anyway, where up here you've got energy of activation and like RT or something like that. I don't want to commit to that because the math isn't important for what we're talking about. But basically, if you increase the activation energy, you decrease the rate constant and make the reaction slower. Okay, so we would predict, if this were the mechanism that's operating, if we were able to measure the rate of the reaction and change the concentration of methyl iodide, we would expect the rate to vary linearly with methyl iodide concentration. Somebody from home is asking, is it just a specific product? Is it one versus the other? You only really have to monitor one because one forms at the same time as the other. But yeah, the answer is yes. Is it one or the other? The answer is both, but you only have to monitor one. So we would expect, as you increase the concentration of methyl iodide, you would expect the rate of the reaction to increase in a linear fashion, and the slope would be the rate constant K. All right. Okay, questions we need to answer so far? What if we increased, in this case, what do you predict if we keep the methyl iodide concentration high and constant, but then we change the concentration of cyanide? Should it matter? No, because cyanide is not part of the rate determining step. Now, I hemmed and hawed there a little bit because I just recently learned in my grad level organic chemistry class that if you lower the concentration of methyl iodide enough, you can start to see some dependence on cyanide. But for our purposes, we're only going to consider what's involved in the rate determining step. And we'll be comfortable in that extreme because cyanide is not involved in the rate determining step. Then we would expect as you monitor the rate and increase concentration of cyanide, you expect to see a whole lot of nothing. Okay, so that's a prediction that we've made, and we can go in and test that hypothesis. And I will tell you that for this reaction, indeed, if you measure the rate and plot it versus concentration of methyl iodide, you do see a linear dependence. However, this is the lack of dependence on cyanide concentration is not what we observe. Okay, we actually observe a linear dependence on cyanide concentration, which tells us that our data are inconsistent with our mechanistic hypothesis. All right? So for this particular example, even though this seemed reasonable, we developed a hypothesis for what the rate of the reaction would be and how it would depend on things. We would predict that cyanide's not involved in the rate determining step, but this is not what is actually observed. Okay. We can talk about why that might be, but let's move on to our third hypothesis. It turns out that our third hypothesis that we make the new bond and break the second bond at the same time is actually going to look a lot like our first hypothesis, only we're going to say that instead of being an intermediate, this is a transition state. So starting materials here, products here. We'll say this isn't an intermediate, it is a single transition state. And in this transition state, what you have happening is Cn minus coming in and making a new bond at just about the same time and to the same extent that I minus leaves. This is almost a hybrid of those. It's almost the average of those first two mechanistic options, right? We're not actually forming a hypervalent carbon. This is not an intermediate. It's a high energy transition state. And we're also not forming a carbocation. We're not forming a carbon that's only surrounded by three things. Instead, but the carbon is sort of flat and sort of sp2 hybridized anyway, as one group leaves and the other group comes in. Okay? In terms of the energy diagram that we would predict for this reaction, you'd have starting materials here and products there, reaction progress on this axis. But instead of going through two different transition states separated by an intermediate, you only go through one. Okay, so with me so far? So let's predict then what we should observe for the kinetics of this reaction. The rate of the reaction, or the change in product concentration with respect to time, is going to depend on, it's going to have a rate constant, and then it's going to depend on the concentration of the things that are involved in the rate determining step. And for this mechanism, both Cn minus and methyl iodide are involved in that rate determining step. So we predict to see a dependence on both. Okay? So what that means is when we do the experiment where we keep cyanide concentration constant, but increase methyl iodide concentration, we're going to see a rate that varies linearly. If I can pretend to draw a straight line. And I'm sorry, this is our methyl iodide concentration. And similarly, if we do a second experiment where we keep methyl iodide concentration constant, getting ahead of myself, but vary cyanide concentration, we also would predict linear dependence on CN minus concentration. And for this particular example, this is what we actually observe. So the kinetic data tell us that of our three mechanistic hypotheses, recall that the first one was that both bonds form, that we make the new carbon-carbon bond first, and then we break the carbon iodide bond. We were uncomfortable with that because we don't anticipate this to be a stable intermediate. Because we don't think that's a stable intermediate, I didn't bother to talk about what the kinetic predictions would be here. It would honestly depend on whether you predict the first one or the second step to be rate determining. But we can rule this out. The second mechanism seemed more reasonable, but it predicts that there would be no dependence of the rate on the amount of cyanide present, and that is not what we observe. Instead, we observe kinetics that are consistent with this mechanistic hypothesis where we're forming the bond between carbon and cyanide and breaking the carbon iodide bond at the same time. Okay. Yeah, go ahead.
So is the difference between a transition state and an intermediate just that a transition state is like a peak on the energy diagram?
Yep. Intermediates are, this is a good question. A transition state is an energy maximum, and an intermediate is an energy minimum. And you can think of it, yeah, as peaks and valleys. Mountaineering actually works pretty well for understanding these kinds of analogies. A transition state is the point where you have equal probability of going forwards versus backwards because you're at the top, and either way you move, you're going to roll down the hill. Intermediates, though, are and energy minima are the positions that are in equilibrium with each other. Transition states determine kinetics. Energy minima determine thermodynamics. So there's a question about, how are you going to know what's observed versus not observed? I'm just, for all you know, I'm making this stuff up. We're going to learn some principles that are going to allow us to predict pretty accurately what is observed in the lab, though you'll find reality will always be more complicated than what we expect it to be. In any case, once you've learned these principles, you'll be able to answer questions where you predict what the products of the reaction are or predict what the mechanism is. Yeah?
Are we going to deal with second-order reactions?
Yeah, so the question is, are we going to deal with second-order reactions? This one that we've just presented is a second-order reaction. We talk about kinetics, and sometimes people use the term order of a reaction to describe how many concentration terms are in the rate law. A reaction where the rate law has two concentration terms is often called second order overall because there are two concentration terms. We would say that it is first order or linear in methyl iodide concentration, and we would say it is first order in cyanide concentration. second order overall. And another equivalent term for second order is that the reaction is bimolecular. That is, there are two molecules in the rate determining step, in the transition state of the rate determining step. Yeah.
So would we say that the rate of conversion of products to reactants dependence first, it depends first and foremost on the activation energy and then on the concentration of your products?
Yeah, so the question here in class is, does the rate depend first on activation energy and then on concentrations of products? The activation energy influences the rate constant, and then concentrations are part of that too. That's not a great answer to your question. I suppose you can think of it this way. Maybe we're presenting these energy diagrams in a sort of standard state kind of position, and maybe if you change the concentrations, that's the same thing as changing the activation energy. And if you increase concentration, maybe that's the same thing as decreasing the activation energy barrier. I don't think that's technically true, but I think it's a sensible way of thinking of things. In a lot of ways, reactions happen when two molecules collide with each other. If you increase concentration, you're going to increase the frequency of those collisions, which makes it more likely for a reaction to happen. So I guess I would answer that no, one is not more important than the other. They all affect the rate of the reaction. Yeah?
So did you just know it was first order with respect to like cyanide and the CH3I because you just know that, or is there something you recognize?
So do I just know that? Well, first of all, no, when starting out, nobody knew that. They did experiments to demonstrate that it's the case. But I think you're getting to the question of why does it have to be that way?
Well, just in the predictions, because like if it were second order with regard to one, obviously it wouldn't be linear.
Yeah.
Like our predicted. So is there something you recognize in the predicted it's going to be linear?
Okay. So I think the question in class, if I'm understanding it for you folks at home, is related to how I knew that it was going to be this second or this third scenario instead of the second one?
No, more so as you increase the concentration of one, it's a linear change of rate versus...
Okay. So the question is, how did I know that as I increase the concentration of one, I'm going to see a linear increase in rate? There's a difference between what I'm saying we predict and what I'm saying we observe. Observations are just that. They just are. But what I'm telling you is if I predicted that the rate law would look something like this, just mathematically, if I plot rate versus concentration of this, it has to be linear. Because it's a direct proportionality. I guess what I'm saying is in this experiment, I'm keeping Cn minus concentration constant. So it's like that goes over and becomes part of this big constant, and then all you've got, if you plot rate versus this, is a linear relationship. Now, if for whatever reason there were some weird mechanism where two molecules of methyl iodide were in the rate determining step, you wouldn't see a linear dependence. You'd see something different from linear, something higher order than linear. And there are cases where you observe strange things like that, but not typically for the reactions we'll be dealing with. Did I
Yeah, that makes
more or less get that? Okay, others. So I will point out that scenario 2 that we talked about, this proposed mechanism is first order. It only has one concentration term. And we would also call it unimolecular. And it's a legitimate option, but it's not the option taken by this molecule, all right? Why does a molecule take one mechanistic pathway versus another? That's the same question as asking, why do you take one pathway versus another when climbing up a set of hills, right? Do you climb the higher hill Okay, let's assume you have no motivation to see what's on the other side. Your goal is just to get from A to B the lowest and laziest way possible. You're going to take the lowest energy pathway. And for molecules, they have no agency as far as we understand the term. They're going to take the lowest energy pathway possible. And so for this set of molecules, it's actually easier, the transition state to go over this reaction mechanism in one step is actually lower in energy than it would be to do it stepwise. That's in this particular case with these particular players. We can do things to either player, the nucleophile and the electrophile, that are going to change that situation. And that's at the heart of what we're going to be doing in Chapter 7, figuring out what is it about the nucleophile versus the electrophile that makes the unimolecular pathway better than the bimolecular pathway or vice versa. All right, sorry, we went too long. It's a good enough place to end. We'll have a great weekend, and we'll see you on Monday.